All right, what we're going to be looking at right now is data organization and analysis. So your objective here is to create and analyze tables and graphs. Why are we doing this? Who cares about it? You should care about it because pretty much everything that you buy has to go through tests before you are able to buy it. So those awesome headphones that you got for your birthday or whatever, okay, they all went through tests. And in order for you to be able to figure out which product is actually the best at what it's supposed to do, you need to be able to look at data tables and graphs and figure out whether it is actually better than another product or whether somebody is tweaking the data in some way to actually make it look like it's better when it's really not. If you can't read the data on your own, you just have to rely on what somebody else tells you, which is never a good thing to do. So the first thing we're looking at is the data table. All this is a way to organize your data from an experiment. So when you draw a table, usually your independent variable is going to be in the left column, and the dependent variable with different trials is going to be in the next columns to the right. So remember, columns go up and down, and your rows go side to side. So your very first column over here will be your independent variable, and then your dependent variable will go over here. So your number of columns should equal the number of trials plus 1, and your number of rows should equal the variations of the independent variable plus 1. So in order for you to understand what I mean by that, let's look at an example. So if you are measuring the effect of sunlight on plant growth, your independent variable in this experiment, what you're changing is the amount of sunlight. So that should go in your column all the way to the left. You are going to measure 3 different amounts of sunlight in this experiment. So that means you should have 3 plus 1 or 4 rows. So you would go ahead and draw 4 rows. Remember, rows go across. You're going to make 4 different measurements. Okay, so these are going to be our columns. So in order to figure out number of columns, take your number of measurements, in this case 4, add 1, you need 5 columns. Okay, finally you're going to make sure you have a title. So if we're looking at our graph here, we have 3 plus 1 rows, right? 1, 2, 3, 4, and we had 4 plus 1 columns. So 5 going across. We've got our amount of sunlight 3 times and our 4 measurements here. The title, you can draw a box around, you don't necessarily need to, but you do need to make sure that you have a title and make sure that your labels here are correct. These empty boxes here are where your data would actually go. So let's look at a second example. If you are measuring the effect of temperature on bacterial growth, you want to have one group of bacteria at 15 degrees Celsius, one at 25 degrees Celsius, and one at 35 degrees Celsius. That's your independent variable. All right, so that's going to go in your column all the way to the left. Okay, so you're going to have your title up at the top, which would be temperature, and then your 3 temperatures, 15, 25, 35. So again, 3 plus 1 rows. Then you have your number of measurements. You're going to make a measurement after 8 hours and then after 16 hours. So 2 plus 1 would be your number of columns. So in addition to your column that you just drew for temperature, you need 2 more for your 8-hour and 16-hour measurements. So at the end, you'll end up with a table that looks like this. And if you don't get the first try correct, it's no big deal. You can always add on a column, delete a column, whatever you need to do. Just make sure that at the end of everything, your data table is correct. Okay, graphs. Data tables are great for organization, but they don't really allow us to see patterns or trends. So that's what we use graphs for. We can see, oh, this is obviously increasing, or this is not increasing here, and then all of a sudden increasing here. It shows us what is happening in a visual way. Generally, you will use a lot of line graphs in science. They are used to show a change over time or distance, could be over days, weeks, minutes, seconds, whatever it is, but any change over time. Bar graphs are used to show differences between categories. Parts of a graph, things you need to know. Take a look at this diagram here. You need to be able to read stuff like this. You have your y-axis here, goes up and down. X-axis, left to right. You've got your labels on your y-axis and a label on your x-axis. Those are important. You're going to need a title, and then you have your scales here. So let's look at each part of this. How do you know what to put on your x or y-axis? Okay, independent variable is always going to go on the x-axis. You can make an eye with it. See, it fits. So remember, independent variable is what you're changing. Goes on the x-axis. Dependent variable then goes on your y-axis. Okay, you can draw the letter D there. This is what you're measuring. Okay, you can't draw the letter D on the x-axis, so it does not go there. It goes on the y. Make sure you have a title. Just needs to be simple. All it is showing what is in this graph. Your x and y axes also need a title with units. So don't just tell me, oh, it's the height of the plant. You need to tell me, did you measure the height of the plant in centimeters? Did you measure it in meters? Did you measure it in number of pencils? Okay. Time would be another example. Maybe you measured it in seconds. Maybe you measured it in minutes. Maybe you only measured it once every week, so your measurement would be in weeks. Doesn't matter what it is, you just need to put it on there. Scale is also important. Don't draw a tiny little graph like this when you have all this graph paper to use. Okay, first of all, if someone's reading this graph, it's going to be really difficult to figure out what your measurements are. And second of all, it looks really messy. So use all the space you have. And also, as another part of scale, make sure it's evenly spaced. So if you decide 4 blocks means 10, then 4 blocks needs to mean 10 all the way up. A key is important if you have more than one set of data. So if you have different things that you're measuring all over a particular time period, then you can either use different colors or shapes like over here to show what your data is. And always make sure there's your key right there. It says the blue is this, the red is this, the green is this. All right, looking at some examples. The table shows the number of men and women participating in the NCAA championship sports programs from 1995 to 1999. You also have this data in a graph. So your question is, oops, sorry about that. Your question is, has the general trend of the difference between the number of men and the number of women participating in NCAA sports increased, decreased, or remained fairly constant? So we can see here in our graph, men are in yellow, women are in blue. So we want to know, is there getting a bigger difference here, or is the difference between men and women getting smaller as we go from this side of our graph to this side of our graph, 95 to 99? And if you look closely, you can see that the difference in the height of these two bars is getting smaller as we go along. So our answer here would be that the difference between the number of men and women decreased. Another question, how many more men than women participated in sports during the 96-97 school year? You can either look at your data table here. This will give you a more accurate estimate. You could also look at this on your graph. Okay, see, men, that's about 200,000. Women are in blue. That's about 130,000. Okay, 200 minus 130 is about 70,000. Very close to what we had here in our data table. Last question on this one. What was the total participation among men and women in the 95 to 96 academic year? Here's our answer here, 331,634. Where'd we get that? Data table. Okay, 95, 96. Just take your men, subtract the women, add the women, and you get your answer here. If you didn't have this data table, you could still look over here and again estimate. Well, there's a little bit over 200,000 men and about 125,000 women. Add those together, you'd get something pretty close. So even if you don't have the table, you can still use the graph to answer this question. All right, here's a line graph. Estimate the change in enrollment between 96 and 98. Here's 1996. We have our years down here. 1998. In 1996, we're about halfway between 14.2 and 14.4 million people enrolled. So 14.3 in 1996. In 1998, we're at about 14.6. So subtract the two. That's your change. 14.6 minus 14.3 is about 0.3. Number 5, if the rate of growth between 99 and 2000 continues, predict the number of people who will be enrolled in higher education in the year 2003. Easiest thing to do here is continue your slope. So the rate is shown by your slope. So continue your line all the way across here until about where 2003 would be. And then add up your lines here to see how tall that goes. Best answer here is about 15.4 million. All right, second part of this is CER responses. Our objective with CER responses is to make and support a claim with evidence and reasoning. So this is being able to tell somebody your opinion and then prove that you have a right to that opinion and you are correct. So let's say you've been working a job for a while, you work really hard, you think you need a raise. If you go to your boss and say, hey boss, I want a raise, the first thing they're going to say is why? Right? This is helping you learn how to make arguments like that. You need evidence as to why. I always come in on time. I always do my work. I fill out all my paperwork. Blah, 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 blah. Okay? All of that is reason to support your claim. So that's what we're going to be practicing with the CER. Those are the 3 parts. Claim, it's just literally what you say. Evidence, something to support that. And reasoning connects your evidence to your claim. So we're going to look at these in just a second in a little bit more detail. So your claim is a statement or conclusion that answers the original question or problem. So for example, sleep has no effect on memory. That would be a claim. This trait shown in the pedigree is dominant. Claim. Boom. Very simple, to the point. The next part, what you need is evidence. Why is that claim true? You can have either qualitative observations or quantitative numbers. Okay, but it has to be appropriate and sufficient to support the claim. So you can't say, hey boss, I want a raise, and he say why, and your evidence is, well, I come in on time 4 out of 5 days a week, right? That's not good. Or you can't say, well, I'm really good at beatboxing. That has nothing to do with why you need a raise, okay, unless that's your job. But so example, students who slept 8 hours after studying remembered 70% more vocabulary terms than students who slept only 5 hours. Okay, that would be a quantitative piece of evidence. Every person in this pedigree with the trait has at least one parent who also has the trait. Also, 2 parents with the trait had a child without. That's qualitative. Reasoning, this is your justification that connects the evidence to the claim. So it shows why your data counts as evidence. So you could say, for example, boss, I deserve a raise. I come into work on time every day. Therefore, that shows I'm responsible and I care about my job. So I should get a raise. Okay, so that's your reasoning at the end. You can use diagrams here, not necessary, sometimes helpful, but always make sure, even if you include a diagram, that you explain it in words as well. So your examples here with the same claims. If students who slept more remembered more, then memory must be affected by the amount of sleep. Okay, and then you can read your own here. I'm not going to read that one to you. All right, so here's your rubric that you're going to be graded by. You can read that on your own. Always check yourself before you hand in your papers. Okay, you're going to have a CER to do on every summary sheet for every unit that we have. Here's an example of a CER. Cockroaches prefer dark environments. They want to hide from us. Because cockroaches have these long antennae, maybe they can just feel their way around and don't need light to see. Okay, claim I would say is okay. That's a decent claim. They might get a 3 on that claim. They want to hide from us. That's not really evidence. Not so great. Okay, so if we were to grade this one with the rubric, it would probably get a pretty low score. This one is a little bit better. We can see they actually have data. 10 cockroaches chose between the light and the dark. 9 of them chose the dark, so they must prefer the dark. Okay, it has data. What you're going to do now is practice writing your own CER response based on this prompt here. All right, so why does the graph tell us which fertilizer is correct? So your claim should be A or B, increases plant growth the most, and then explain why. All right, when you're done, grade yourself with your rubric and see how you did.